The most important sampling concept in Bayesian machine learning and Bayesian analysis uses Markov chains. And in this video lecture, we will review the major concepts for Markov chains. So Markov chains are defined over sets of random variables, and they're random variables that we think of as occurring in time. So for example, let's say we have a set of random variables designated here as xn, where n is going from 0, possibly up to infinity. And we can consider at time 0, for instance, to be the start of the process, time 1 to be the next point in the process, time 2 the next one after that, and so forth. So at each point, we get the value of a random variable, and we're designating that by x sub n. And that value comes from some discrete set. And again, we'll consider these to be counting numbers. And we show that by block n. So in this space from which they come, this set of counting numbers is the state space. So for example, a common state space is 0, 1, a binary state space. So we could consider that, for example, to be, did it rain today or did it not rain? Where a clear day would be considered 1 and a rainy day would be considered 0. So we could say it rained today, 0. It rained tomorrow, 0. The day after that, it was sunny, and so as a result, it was a 1. Or we can consider the random variables to be the performance of a stock. Did the stock price go up? Did it go down? And again, we're counting it over time. So the X3, for example, would be on day 3. The stock went either up or down. So was it 1 or 0? And they could be any number of from this counting set. So we could have 3, 4, 5 different states. We could be looking at the condition of a patient. Were they in normal condition today? Yes. Did they? And so we could consider that to be 0, for instance. Did they have the flu? That would be 1. Did they have a cold? That would be 2. And so the condition of the patient and their illness over a period of time would be this. The state space would be their condition, and over time they would define this set of random variables. So the way a Markov chain works is basically a straightforward use of our notion of conditional probabilities. So if we consider the probability, let's say at some period n plus 1, some time period n plus 1, and it's in state j, whatever that state is, well, that will be conditioned on all the previous states in the process, all the way back to the beginning of time. But it turns out for a Markov process, it's independent of all the previous states except for the state just before the current time. So if we're currently at time n plus 1, then the only thing it depends upon is the previous time period, which is state n. And this is called a Markov property. And sets of random variables that are these processes that are indexed by this index of positive integers are called Markov chains. So something that has this conditional property that basically says it's only the value today is only dependent on the value yesterday is then a Markov chain. And this Markov property you can see is a nice generalization of independence. An independent state would say that all those states are independent. So again, if we think of our rain, no rain example, we'd say if it rains today, it's independent of whether it rained yesterday. And in fact, we know that that's really not true. That if it rained yesterday, it's more likely to rain today. And so this idea of a Markov chain and the Markov property actually has real applications. Same is true of stock prices. If the stock went up yesterday, it's most likely it'll go up tomorrow. So it's one of these things where we look at stock prices, we look at weather. These things behave as according to this Markov property, which is a very convenient way for us to model a lot of things in the world. It's not as rich as modeling all points in the past, but then frankly, that makes the mathematics of it very complicated. So a Markov chain is a simple generalization from state independence to and statistical independence to the notion of dependence, but only in the previous period. Well, with that idea, then, we can define one-step transition probabilities, and these are just the probabilities of going from one state to the next. So if we look at the top row in this matrix, these then define the probabilities of going from state 0 to state 0, state 0 to state 1, state 0 to state 2, and so forth, all the way up to the limit. And the second row is state 1 to state 0, and so forth. So we can now, with the idea of a one-step, we can define an n-step transition probability in a very general way. So suppose that the probability in state J after n plus m transitions from state I is what we're after. And we can find this by summing over all intermediate states. And you may not be surprised, but we're going to use the conditioning argument that we've used over and over again in order to get it. So here we go. We want to know the probability of being in state J, given that we started in state I. And the number of transitions that we make in order to go from I to J is n plus m. So we've just written out what this conditional probability means. For example, starting at state 0 at the beginning of time in I, and ending up in state J after n plus m transitions. Well, as I said, we're going to use our good old conditioning argument and just condition on the state we're in at time n. And suppose that state we're in is k. Okay, so we've started at I at time 0. At time n, we're in k. And now the question is, what's the probability that then we're in state J? Well, we can find that by summing over all these states k, because that's the conditioning argument or the sum rule. We're just going to sum over all that intermediate state. And now we just use our definition of conditional probability, because notice that we have a joint probability in the first sum, and now we just break that into a conditional probability times the marginal probability. So the conditional probability is in being in state k at time n, and the marginal probability is being in state k at time n, given that we started in state I at time 0. And notice that conditioning on xn being in k and x naught being in I, well, because of the Markov property, that x naught being in I goes away. And the only thing that matters is that at state n we were in k, and the question is, do we go to state j with an additional m steps? So now we can just write that in terms of these matrix properties, and that's just going to be the transition in n steps from I to k, and the transition in m steps from k to j. And again, we've conditioned on being in k, and k has to go over all possible values. Let's find what these n-step transitions are. Let's work out the computation of them. So we're going to let P of n be the matrix of n-step transition probabilities with the parentheses now around the end. And it turns out that that's just that matrix, the one-step transition taken to the power n. That's all we have to do is just multiply it by itself n times in order to get the n-step transition matrix. So for example, let's take the case of weather. We've got a two-state Markov chain, so that if it rains today, it rains tomorrow, let's say with probability 0.7. And if it's sunny today, then it's sunny tomorrow with probability 0.6. So the question is, if it rains today, what is the probability it rains in 2 days and in 4 days? Okay, the one-day transition or the one-step transition matrix we can easily get from the definition of the problem, and that's shown here. And if you go back and look at the previous description of the problem and satisfy yourself that we've written this out. Remember again that first row in this matrix, 0.7, 0.3, This is the transition probability, the one-step transition from state 0 to state 1, probability 0.7, state 0 to state 0, 0.7, state 0 to 1, 0.3, okay? And the second row is transition from 1 to 0, 0.4, and 1 to 1.6. Okay, in 2 days, we just take that matrix and square it, and just do that, and there's the result. And in 4 days, we square the previous result, and here's what we get. Now take a look at that matrix, and I think you'll notice something. And if what you notice is that the columns have the same values, 0.57 in the first column and 0.43 in the second, you're noticing something very important, and we will see why in just a couple slides. Okay, Markov chains have their own jargon, and we're going to define that jargon now. So the first notion is accessibility, and we say that state J is accessible from state I if the probability of going from I to J in some n, again for n greater than or equal to 0, if that probability is greater than 0, then we say that it's accessible. We say that states I and J are accessible. If states I and J are accessible from each other, then they communicate. So we can go from one to the other, then there's communication between them. Okay, a Markov chain is called irreducible if all states communicate. So if every state communicates, then it's irreducible, which means that there's no disjoint states that are just off by themselves or separated from other states. And you can't get from one part of the Markov chain to the other part. So let's let GI be the probability that starting in state I, the process will eventually re-enter state I. So we start in state I, and the question is, do we ever re-enter it? And we're going to let GI be the probability that we do. So we say that a state is recurrent if GI is 1. In other words, we will absolutely at some point come back to the state, one of these states that we started. Any of the states in the Markov chain that we started in, will we come back? And if we don't come back, if it's not 1, then it's called transient. So state I is positive recurrent if starting in I, the expected time to return is finite. So, okay, the probability that we return in some infinite time may be 1, but that's not so interesting. We want to know what it is if there's a finite expectation of return, and that's notion of positive recurrence. And it turns out that a finite state Markov chain, which means that we don't have a number of infinite states, there's only a finite number of states that it can be in, okay, so it's some fixed number. It could be large, but it doesn't matter. It just has to be a finite state. Then all recurrent states are positive recurrent. So in other words, their expectation of return is finite. Okay, a couple more definitions. So if we've got now the probability we start in I and we return to I for n, for some n, and if that n is not divisible by d, where d is the largest integer with this property, then we call I periodic. So in other words, we're not going to be returning in a cycle, or we will return in a cycle to this state. And if in fact that is the case, that this cycle length is the largest it can be, so that's this largest integer, d, is 1, then it's called aperiodic. So there are no real cycles in here because this is a finite state Markov chain with a finite number of states, which means that we basically are going to go from one state to the next, okay, over this these periods of time. And if there's the largest integer that we have a cycle in is 1, that means effectively there's no cycle for us. Okay, there's no additional cycles. So this aperiodicity means that we've got no cycles in the Markov chain. So a positive recurrent aperiodic state is a Markov chain with that property is called ergodic. and the states in that chain are called ergodic. Okay, so now we go to the important theorem that we have that gives us our limiting probabilities. And so the limiting probabilities are over all time, where is it that we will end up? Which of these states are we going to end up in? Okay, and in particular, we want to know what the probability is of being in any of the states. So what's the probability it's raining? What's the probability it's sunny? Okay, over all time. So if you look over, all time being many years, what's the probability that in your town it rains or in your town it's sunny? That's what we're after here. Or what's the probability over all time that the Standard & Poor's goes up and the Standard & Poor's goes down? The Standard & Poor's index goes up or goes down? So those are the kinds of questions that we're interested in. What's the long-term probability of being in any given state? Okay, so for an irreducible ergodic Markov chain, these long-term probabilities exist, and they don't matter where we started. Okay, it doesn't matter where we started. The only thing that matters is we're looking at the probability of being in that state. So it's completely independent of the starting points. And it turns out there's a simple set of linear equations that solve it. The first shows that we can just take and find those long-term probabilities weighted by the one-step transition probabilities. And of course, these long-term probabilities have to be probabilities, so they have to sum to 1. Now, I've shown this over an infinite number of states, but in fact, for most practical problems, obviously we don't have an infinite number. We have a finite number, and that's what we're concerned with. Okay, so let's look at our rain and no rain example again to see how this works. So here's the solution to the problem. To find these long-term probabilities of rain, no rain, we just, again, write it exactly as it says in that those equations, that it must be the case that the weighting of these long-term probabilities by their transition probabilities defines each one of the independent long-term probabilities. And we'll also see that these probabilities must sum to 1. And notice that the probabilities from the states sum to 1. So in other words, if we look at that first, the weight on pi 0 in the first equation, that's the one-step transition is the probability from state 0 to state 0. And notice in the second equation, it's the transition probability of state 1 to state 0, and we've written it in terms of its its converse, which is 1 minus the probability of going from 0 to 0. And so these probabilities have to add up to 1, which is how we solve for the answer. And here's the solution. Go back, plug in the one-step probabilities, and satisfy yourself that this is the solution. And notice that this is exactly what we found after 4 transition steps with our just doing the matrix multiplication. So these are the basic concepts that we need then for Markov chains. And with this way, we'll be able to build out the most important sampling method for Bayesian machine learning.